weekend in São Paulo. It's a real pleasure to have Professor Andrea J here from the University of Pennsylvania. And she's going to talk about the intersection of data science with soft living disordered elastic systems. It's really great to have you here, even though you're not in person, but it's fantastic that you accept our invitation. Thank you, Andrea. You can go ahead.
Hi, thank you, Danilo, for the invitation. And I am so sorry for many, many reasons. The first of which is that I've actually never been to Brazil, and I was really looking forward to coming. So, hello. And I hope you will all just butt in and ask questions as I go. So, and please let me know if my pace is too slow or too fast. Okay, so, all right. So it's really hard by Zoom, right? So I really hope you'll interrupt and ask me questions so that I know that I'm not talking to avoid. Okay, but I like the camera view on the audience. That's great. Okay, so the first thing, I switched the order of my lectures. So I realized that it made more sense that way and also fitted better in terms of timing. So the first two lectures will be basically applications of data science methods to learning physics. And so first starting with machine learning for learning dynamics in glassy systems. And then the second one is using persistemology to learn about function in networks. And then the third one will be actually about designing metamaterials and learning. Okay, so using machine learning ideas to design metamaterials. So I'm switching this, what were listed as the second and third lectures. Okay, so, right, we're statistical physicists here, all of us. And so, right, our aim is to understand at the microscopic level something about collective phenomena. And when we think about what this requires, just go back to the beginning and think, what are we doing when we do statistical physics, right? Well, first of all, we're taking a huge amount of microscopic information and distilling it down just to a few relevant microscopic variables. So that's a huge dimensional reduction problem that we're doing. But we're also, there are two parts to it, the dimensional reduction, but also finding that bridge from the microscopic and macroscopic scales through the right relevant, the right microscopic variables. Identifying what those correct microscopic or useful microscopic variables are. So, so what I'm going to talk about is a class of problems that have resisted the traditional approaches in statistical physics. And exhibit A, when you start talking about this, is the glass transition, right? So, so the glass transition is actually still highly controversial. And even though I'm part of a Simon's collaboration, which is called Cracking the Glass Problem, I can't say that we've cracked it, but we've made some progress. So it's a very hard problem, and let me explain why. So, right, the whole difference between liquids and solids is that liquids flow, solids don't. And what do we mean by that? Well, if we apply a stress to the system, right, eventually that stress will relax in a liquid. And how does it relax? Because the particles, instead of holding that strained configuration, they will change their neighbors. Okay, and that's how the stress relaxes away. And that those rearrangements, those at the microscopic level where particles change their neighbors, are that mechanism of stress relaxation. Now, if we call the time that it takes for that stress to relax, the relaxation time tau, then what happens if you have a freezing transition, right? Well, if you have a freezing transition, right, where the constituent molecules, for example, water, are disordered in the liquid and then become ordered in the crystal, the relaxation time will jump discontinuously at that freezing transition. And that's, so that transition is marked by the onset of order and by discontinuous jump in the relaxation time. So in that case, a microscopic variable that will tell you about that transition, right, is something that characterizes the order, because it's not there in the liquid and it's there in the solid. And we've understood freezing transitions for a long time. But the glass transition, right, is different because the particles remain disordered. And the relaxation time, as you cool the system, the relaxation time just increases continuously. There's never any jump. And not only does it increase continuously, but extremely rapidly. So it's not uncommon to get 10 orders of magnitude increase in the relaxation time and just tens of Kelvin. Okay, so that's an extremely dramatic thing. And very rapidly, right, what happens is that the relaxation time increases so rapidly that at some point you can't wait long enough for it to relax. And at that point you say the system, of course, has not equilibrated yet because the stress has not relaxed. And at that point you just give up and you say the system's a glass. So this is a universal phenomenon, okay? Every single liquid, if you can cool it down fast enough to avoid crystallization, so nucleation and growth of the crystallites, every single liquid will do this. And because it's a universal phenomenon, right, it requires a universal type of explanation. And why has that been hard? Well, that's been hard because, first of all, there doesn't seem to be an obvious change of symmetry at the transition. You don't go from being disordered to ordered in some variable. We don't have a microscopic variable that reflects a change of symmetry. There is understanding much more now, especially in infinite dimensions, but low dimensions is still a problem. The system is naturally far from equilibrium, right? Once it's a glass, we haven't waited long enough for the stress to relax, so it's not in equilibrium. So the system is far from equilibrium, and it has a complex landscape. So I think you've heard about complex landscapes. Glasses, of course, combine all of these three problems. Any one of these three problems, okay, is a killer. For understanding things through statistical physics, or can be a killer. All three of these together are really a problem. Okay, so I think you've heard quite a bit about complex landscapes, but right, I have a picture of the height versus two position coordinates. We're really thinking about a landscape where we have energy as the height, okay, and versus 3 n position coordinates where n is of order, say, 10 to the 20. So it's a very, very high dimensional landscape. And it has a huge number of minima. So e to the order n minima. So just think, for a system of just 1,000 particles, very easy to do on the computer, right? That's 10 to the 1,000 minima. That's just a mind-boggling number of minima. And we can't possibly understand the landscape or map out that landscape numerically on the computer, right? And the problem is that the properties are inextricably linked to the dynamics in this landscape. Because think about what happens at high temperature, right? You're floating above all the peaks, okay? Any particle can relax at any time, okay? Can rearrange at any time. That's an ordinary liquid. Now, as I lower the temperature to fall among, somewhere among these peaks, right, you can start getting trapped and not being able to go over, saddles into other minima. And so the dynamics of how you traverse this landscape are related to the properties of your system in that landscape. And that's what makes the problem hard. Okay, so now it's time to confess that I lied to you already in just a few minutes, because I said that the difference between liquids and solids is that liquids flow and solids don't. And that is not true at all, okay? Solids can flow, right? So for example, you can bend a metal spoon. When you do that, right, you apply the stress and you bend it, but after what? You don't have to apply that stress to keep it bent. The stress has relaxed. Okay, so the system, there has been flow, and that's called plasticity, okay, when it's in solids. Of course, you can do that to a glass rod or a plastic rod as well, just by heating it up a little bit. It's still solid, but you can now bend it, no problem. Okay. So if I think about solids, and I'm going to later draw a distinction between ductile and brittle failure. And so this is what happens in a ductile solid. And I think you've heard about crackling noise and so forth. But the idea is that at very small strains, you get a solid elastic response. Okay, so that's the difference between a solid and a liquid. A liquid, you don't see the solid response at small strains if you wait long enough. But if you apply enough strain, the system will eventually yield and you'll see this liquid response. Okay, now many solids, you don't actually see this. You see them just break. If you imagine taking a glass rod and just bending it, right, it'll just snap, right? And that's brittle response. What happens is that there's a sudden stress drop and the thing fails. So that's the difference between a ductile solid. A ductile solid, you can have this sort of liquid plastic response over quite a large range of strain, whereas for a brittle solid, you very rapidly, at a very small strain, you see just fracture and failure. Okay, so it's the strain at which, what marks ductility is the strain at which this sort of liquid or plastic response fails. Okay, stops. All right, so in between, but let's just think about ductile solids for a moment. So in between the solid and liquid response, right, you have yield. And so there's some point, there are many definitions for it. It doesn't really matter. It's somewhere in between these two extremes, right? You have the point where it yields, and there's a yield strain and yield stress associated with that. Okay, so go back to what we're trying to understand, right? The idea is, if we're going to, so we've got this thing, we've agreed that, understanding what's happening in this complex landscape, either as a function of temperature as I cool it down. Oh, I forgot to say, or if I'm applying strain, right? If I apply strain, I said there's yielding. What's happening in that landscape when we're straining? What we're doing when we're straining things, right, is we are deforming that landscape. So that what we're doing is we're lowering some barriers until they disappear and you can go over saddles, or they become lower and you can, and they form saddles. So what you're doing when you're straining the system is you're deforming that landscape and being dragged through it by deforming it. Okay. All right, so we agree it's a hard problem. Statistical physics has had a hard time with it in low dimensions. So now what can we do, right? So of course, from the title that the idea is to use machine learning to try to make progress. But how do we use machine learning? What do we focus on? Where do we start? So the idea is to start, again, by thinking about crystals, okay? So if we think about crystals instead of glasses, we know that it's the particles that are defects, specifically dislocations, that are much more likely to rearrange, okay, either due to thermal fluctuations or applied stress. And so here's a nice set of experiments by my colleague Arrhenius at Penn. So these are colloidal crystals, okay? And you can see here the grain boundaries. Okay, so here's one orientation of the crystal. Here they are in a different orientation, and here they are in a third orientation. You see that there are these angles between them. And now, if you heat the system, okay, where does melting start? It starts at the grain boundaries where it's disordered. Okay, so this is heating the system higher and higher. Now, what they're actually doing, it's a cheat to say that they're heating it. Of course, they are heating it, but that's not temperature. That's the important thing in this case. What's happening is as they raise the temperature, the particles are shrinking. Okay, and so they're driving through the solid to fluid transition by changing the concentration of particles, by shrinking the particles. But as they approach the melting transition that way, what you see is that where it melts first is at the grain boundaries, at the defects. Okay, the same thing happens if you apply stress to the system. If you apply stress to the system, it's known that where the system tends to yield, where rearrangements are concentrated is in the defects, not deep in the crystalline regions, but in the defects. And why is that? Well, it's because the energy barriers to rearrange are lower at the defects. Okay, so, and the whole field of plasticity in crystals is, about trying to understand the structure of these defects and how that affects flow. All right, so with that in mind then, knowing that, then the question for glasses, either plasticity in glasses or dynamics of glassy liquids as we lower the temperature, is can we define defects which have lower energy barriers to rearrange? And that was a 50-year-old challenge. People were looking and looking and looking to try to find defects and couldn't really find anything that was convincing to very many people, except their own academic parents or children, perhaps. So, so basically by 2010, people had sort of given up on the idea of being able to find defects from structure. But it turns out that it's incredibly easy with machine learning. And let me, so that's what I'm going to tell you about today. Okay, so it turns out that machine learning provides the right microscopic variable. Okay, and what I'm going to talk about is, first of all, how we define that variable and what are its properties, but then how do we use that variable as the basis for a theory, for a theory of collective phenomena, because it's not enough to use machine learning just to identify something, right? You need to use it to extract physics. And we're statistical physicists. Our goal is to build a theory. So what I'm going to talk about is a theory for dynamics of supercooled liquids and also for plasticity in disordered solids. And I hope by doing this, you'll get a feel for how to do this. Because the problem with machine learning methods is that they're incredibly powerful, but they were developed by computer scientists to do computer science tasks, things like prediction and classification. And that's not always what we want in physics. So, to be able to harness machine learning for our purposes is sort of the underlying idea of these, that I'm trying to get across in these lectures. Okay. So before I do that, let me just take a moment to have this philosophical interlude and just say, okay, we're going to use this then. What we're going to do is we're going to use machine learning to predict rearrangements, because after all, machine learning is good for what it's good at is prediction and classification. And that's basically what we're going to be using, how we're going to be using it. But then what's the point of predicting it, right? As I say, is to understand the glassy dynamics or what controls ductile versus brittle behavior. So there have been various approaches that have been used in the last several years. So our stuff was the first, and we used machine learning to predict rearrangements that happen right away. Okay, at the next instant, are you going to rearrange or not? That was the question that we were asking. Okay, but what other people have done since then is to use machine learning to predict future rearrangements. Like, I'm going to look at structure now. I'm going to look at the system now, and I want to understand a whole relaxation time later. Or if I've strained as far as the yield strain, I want to know, can I predict then, much later, okay, whether this particle is going to rearrange or not? Okay, that's a very, very different question. Still others approaches have been trying to construct the very best predictor of rearrangements in the next instant or later, okay? And you can do much better, okay, than what I'm going to tell you, okay? So I'm not saying that what I'm going to tell you is the best way of doing things. It's not the only way of doing things, okay? It's a way of doing things. Let me explain why we have chosen to do things this way. So the first is that the point is that if you want to predict what happens at a much later time or a much later strain, the behavior from now until then, much later, is very chaotic, okay? Inherently chaotic. So therefore, it's incredibly sensitive to noise. And so the structure doesn't actually provide much information about what's going on. The second thing is that, so that's why our approach has been to say, let's develop a theory based on this instantaneous predictor. And why do I say it's structural? Because we're trying to understand defects, right? Defects are properties of the structure. So the question is, can you look at the structure and say, predict something about the dynamics? So the idea is we'll develop this theory then based on this structural predictor. And we're not trying to predict whether this particle or that particle is going to rearrange at a later time. We're going to predict statistical properties at that much later time, right? Because that's the whole point, that in statistical physics, there's always chaotic behavior. You can't predict individual trajectories. That's not the point. You want to predict statistics of what happens. All right. Another thing about our approach is that, as opposed to others, which do much better at predicting rearrangements, is that ours is based purely on structure, just on how the particles are arranged, okay, relative to each other. So we don't need to know what the potential is. The potential of interaction is between the particles. And that's incredibly important, because if we want to look at experiments at the nanoparticle, colloidal, or granular level that can actually track individual particles as a function of time, in those experiments, we generally do not know the interactions with great precision, not enough to calculate, third derivatives of them, which are required for some of these predictors. So, so that's one thing. We would like to be able to have something that we can apply to experimental data. And finally, we want a quantity that's very fast to calculate. So these are, if I have n particles, they're order of n, whereas many of these other approaches are order n cubed or worse. Okay. So these are the people who have participated in the first part of this story. And I particularly want to single out first Sam Schoenholz and Dosh Chubuk, who were two graduate students. They were friends as undergraduates. Sam was a graduate student with me, and Dosh was a graduate student with Tim Kaxiris at Harvard. And Dosh with Tim was working on using machine learning to do, ab initio calculations. You can do better than density functional theory for electronic structure. Okay, so that's what he was doing. And Sam went to visit him, and they were chatting, and Sam said, I wonder if this could be useful for my problem, which was to find defects in, defects responsible for rearrangements in glassy systems. And so they actually got it, they tried it, and they got it to work with 90% prediction accuracy before they ever told me anything. Okay, so they really deserve the intellectual credit for doing this. Then I also want to particularly acknowledge Sean Rideout, who just left my group. He's now a postdoc at Emory, who did the theory on the Glassy Dynamics. Okay, finally turned this into a theory. Okay, so what are we trying to understand? So we're trying to now just lower the temperature in that complex landscape, okay, and understand what happens as we lower that temperature. So let me just give you a sketch of what happens. So above some temperature, which is called T0, the onset temperature, you just see ordinary liquid behavior. What does that mean? Well, the relaxation time is Arrhenius. What does that mean? It goes like E to some energy divided by temperature, E to the something over temperature. And that's exactly what you would expect for going over an energy barrier that's E, right? It's just ordinary Boltzmann factor behavior. So that's one thing. So that's just ordinary behavior. There's a characteristic energy barrier for going over for having rearrangements. The relaxation is exponential in time. Okay, so there's just a well-defined time scale for that relaxation, stress relaxation to occur, nothing fancy. Okay, and the dynamics are spatially homogeneous, which means that sort of any particle can rearrange at any time. Once you go below this onset temperature, there's a huge change. Okay, so first of all, the relaxation time becomes usually super Arrhenius. Okay, in other words, it goes like E to some energy barrier over temperature, but that energy barrier now, if you insist on interpreting it as an energy barrier, that energy barrier depends on temperature. And it actually gets higher as you lower the temperature. So as you lower the temperature, it's as if you have to go over higher and higher barriers. Okay. The relaxation becomes a stretched exponential, not a simple exponential anymore. And the dynamics become spatially heterogeneous. And let me explain what that means. So first of all, yes, the super Arrhenius behavior, let me just show that to you. So this is a kind of plot that I will be showing. So it's the log, this is viscosity, but you equally well, you can say it's the log of the relaxation time. Okay, so if you have something that looks like this, if I take the log of this, right, it should go like 1 over temperature. It should go like the energy barrier over temperature. So this is the log of relaxation time, essentially, versus 1 over temperature. And if it's simple Arrhenius behavior, you should get a constant slope, which is the energy barrier. Okay, just straight line. Okay, what you see here for many, many different systems, and this is a classic plot going back to Austin Angel, who died recently, who is just a wonderful person, who really nurtured the field. Anyway, you have this super Arrhenius behavior. So where instead of being straight, okay, it curves up a lot. And what that's saying is that the slope, which is the effective energy barrier, is increasing, okay, as I lower the temperature. So that's what I mean by that super Arrhenius behavior. There are actually strong glass formers. Those tend to be network glasses like ordinary window glass, okay, tend to be nearly Arrhenius in their behavior. But most molecular glasses are super Arrhenius, strongly super Arrhenius. Okay. So this is what I mean by the onset of super Arrhenius behavior. So above this onset temperature, so this is the log, the temperature times the log of the relaxation time. So again, if you have something like this would just be the energy barrier E. So above the onset temperature, you see it's constant with temperature. It really is just an energy barrier that's constant with temperature. And you see this behavior. But if you go below this onset temperature, you see it start to shoot up. Okay, so that's the energy barrier getting higher as you lower the temperature. I talked about the differences, exponential and stress exponential behavior. Again, you can look at it here. So if you look at, this is the relaxation time. This is a measure for it. I'm not going to go into what measure it is of the relaxation time, but it's the decay of this, the time scale decays for this function to which characterizes the structural change to go from 1 to 0. Okay. And it goes as a stretched exponential. And that if you look at that stretched exponential, okay, at high temperatures, it's around 1. Okay. But below some temperature, it starts to decrease. Okay.
Hey,
That
Andrea, we have a question here.
The same as the onset temperature for the energy barrier to start increasing. Okay.
We have a question here, Andrea.
Yeah.
Just a second.
Yeah.
Thanks. I was wondering, does it just look like the energy barriers increase, or are they actually increasing? Or is it just because the temperature is lower, there's just less probability of jumping to one to the other?
No, it's not just that the temperature is lower, because if it were just lower, then it would be harder to jump over the energy barrier according to this, right? This would be enough. But it's more than that. The energy barrier actually seems to be increasing as you lower the temperature. So it's as if you're falling into deeper and deeper parts of the landscape. And yeah, I will come back to that, and I will talk about that and what that's saying. Okay, so it's not just that the temperature is lower, because that you could handle with the Boltzmann factor. Okay, it's that. By the way, I'm still calling it Arrhenius in my talk, but I actually hate Arrhenius now. I didn't know this story, but when Marie Curie was awarded her second Nobel Prize, he was the president of the Swedish Academy. So, but she was embroiled in this scandal because she had an affair with Langevin. Langevin was married. She was not married. She was already a widow. Langevin was married, and there was such an outcry in France, they almost deported her back to Poland, even though she had a Nobel Prize. And Arrhenius got in touch with her and wrote her a letter and said, can you please turn down the Nobel Prize? We're awarding it to you, but I'd like you to turn it down to spare the Nobel Prize the scandal. And she refused. Good for her. So anyway, so I'm sort of mad at Arrhenius. So let me just call it Boltzmann behavior or super Boltzmann behavior. So it's not just that the temperature is getting lower. Okay, it's more extreme than that.
We have another question.
Yeah.
I know that in these Arrhenius and super Arrhenius, it's not covered, but could you comment a little bit about the volume dependence of this energy barrier as you lower the temperature or even when you apply stress?
I just could not quite hear that last question. Can you just ask that question again?
Could you briefly comment about the volume dependence of the energy barrier when you lower the temperature or even when you apply stress?
The volume dependence?
Yes, that's what he asked.
Yes, it's very strongly volume dependent. So, the experiments, but you see it whether you fix the volume or the pressure. You'd still see super Arrhenius behavior whether you fix volume or temperature. But there is a very strong volume dependence. It's very strongly density dependent. And so as you increase the density, the barriers get higher very rapidly. That's because it's the hard cores of the particles, right? You're getting into that 1/r to the 12th part of the potential. It's very, very steep. It's those repulsions that are very strong. And so that's seen experimentally. There are beautiful experiments done looking at the density dependence of this by Christian Alba Simeonesco, I don't know, maybe about 10 years ago. Very nice experiments. Yeah, that's a good question. These are very strongly volume dependent. Okay, so that's the stress exponential. We see them, the onset at that same temperature. And the last thing is the spatially heterogeneous dynamics. So let me just explain what they mean. And the easiest, it's seen in all of these systems, but I'm going to show you it in the context of an experiment done by Doug Durian at Penn. This is a granular system, and it's fluidized by the grains are little ball bearings. They're floating around on a wire mesh, and there's gas flowing up through this mesh. As the gas flows up through the mesh, it becomes turbulent, the flow becomes turbulent, and those little turbulent wakes push the particles around, and they behave as if they are thermal. Okay, you can do, there is actually, in many senses, a well-defined effective temperature for these systems. So now this is what happens, that effective temperature gets small as you increase the concentration of particles. What I'm going to show you, these are, what you see here are the particle tracks. And they're the particle tracks over a period of time, which is the relaxation time, okay? And what you see is that some particles, which are blue, okay, have very short tracks, whereas other ones that are more reddish, okay, have very long tracks. And so that's how far they travel in this given interval of time. And if you look now at this video of these things, you can see that the dynamics are really heterogeneous in space. And some particles are moving a long ways, very mobile, whereas other particles are essentially trapped in place over the whole time. So that is something that those spatial heterogeneities appear right around that onset temperature, okay, and they get stronger and stronger as you lower the temperature towards the glass transition. So that's another thing that we want to understand. Okay, now what happens if you keep going? Well, if you keep going, lowering the temperature, eventually, as I said, you fall out of equilibrium and you have the glass. And in the glass, the dynamics are spatially heterogeneous. The other thing is the relaxation time depends on how long you wait. That if you look at when did you fall out of equilibrium, okay, so you do a quench from above some temperature down to below the glass transition, okay, so you know when you fell out of equilibrium, and now you look at the time since you fell out of equilibrium. That's the age. Okay, and what you see is the relaxation time gets longer and longer as the system ages. The energy barriers get higher and higher as the system ages at a fixed temperature. Okay, that's in the glass. Okay, so now finally, let me explain what do we do. So we use machine learning then to try to find a structural quantity that tells us about the probability that a particle will rearrange, okay? And the whole idea of machine learning, right, is you don't just look at one quantity to characterize the structure. You don't just look at, you know, how big a person's nose is relative to the width of their face to say, this person is John, okay? Right, to identify the face. You look at many, many, many different things. And and then what we do is we're going to use a very small subset of the data and data that is not structural, okay? We're going to use dynamical data to infer a linear combination of quantities that correlate strongly with particle rearrangements of structural quantities. So in the end, we'll have a structural variable, but we're going to use dynamical information to get it in the first place, okay? And then the idea is that we'll get our physical intuition about what this variable means afterwards, after we've trained it. So what do? So basically, what we look at is the pair correlation function, okay? So we look at the number of particles that have their centers at some distance r away from our central particle. So if I'm trying to characterize the local structural environment of this red particle here, I'll look at how many neighbors I have at each distance r away, okay? Or what's the probability of finding a particle at distance r away? And so we do this at many different values of r, right? So you can think about this, you know, in terms of discrete bins. Okay, I just bin r into discrete bins, and I'm going to just look at the probability of finding a particle at that density. And then the point is we construct a high dimensional space. So on the x-axis, I'm going to put g of r, the probability of finding a particle at one value of r. On the next axis, orthogonal axis, it'll be g of r at a different value of r, okay? And then a third axis will be g of r at the third value of r. So in the end, suppose I have 100 different values of r, 100 different bins, I will have, you know, a 100 dimensional space, okay? A very high dimensional space. Now, the idea is, and, you know, from a physics point of view, like, ooh, you know, these quantities aren't uncorrelated, but by putting them in orthogonal directions, I'm treating as if they are uncorrelated, but in fact, they're very highly correlated, okay? The whole computer science thing is, don't worry about that, okay? Let's just treat them as independent quantities and construct this high dimensional space and see if we can do it, okay? So, so now what we do is we take each particle, then its local structural environment is represented by a point in this high dimensional space, because it says, okay, how many particles do I have at this distance? You know, what's the density of particles at that distance, et cetera, right? So it's the G of R, the local pair correlation function for each particle is a point in this high dimensional space. And now you take these points and you color them. They're either white or gray here. And the white is they rearranged in the next instant. Okay? Gray is particles that haven't rearranged for a long time, for a relaxation time in the past. They have not rearranged. So this is where I use dynamical information, is in the training. Okay? And then you say, what's, you know, can I draw a hyperplane in this high dimensional space, okay, that divides, that best separates white from gray? Okay, so if I have an m-dimensional space, I want an m-1 dimensional plane that separates white, best separates white from gray. Now, first I have to tell you what is a rearrangement? How to identify a rearrangement? Because we're going to use that dynamical information. And so you can use various things. You can use, one indicator is p-hop, which is what's the particle position at t minus at 0, the distance, okay, between the particle at t and the particle at time 0. And you can see that, you know, it doesn't move very much, and then bam, it can hop, right? And you can see these hops. One thing I have to say is that we take snapshots of the supercooled liquid, and then to get rid of thermal noise, we do one of two things. We either quench it down to 0 temperature. So we just instantaneously just quench down to 0 to the nearest local minimum and look, that's called the inherent structure. And we look at that and we compare what's happening in the inherent structures. So if you're still in the same basin in that complex energy landscape, your particles will not have moved at all, okay? And then if you jump into another basin, you see this big change in p-hop. So that's one way to do it. Another way you can do it is by a time average. So that's something what we do. We just average over, you know, a bunch of collisions of this particle and thermal collisions of this particle, okay, against its neighbors. And if you average, again, you average out that thermal noise and you can see this, okay? Either way is fine. So that's one indicator. Another one that I'm going to come back to a lot, okay, so I want to get it out of the way now and explain what it is. It's called d squared min. And what it is you look, I have my central particle and I look at it some neighborhood, some distance from around it, typically about 2.5 particles, okay? And what you do is you take that neighborhood and you fit the best strain tensor that you can to this, assuming that there's just a homogeneous deformation of this. Okay, so you fit the best strain tensor, that's lambda min, and then you look at fluctuations of the positions around that strain tensor, because each particle is not where that best fit strain tensor is. There's some deviation from that. You look at the mean squared deviation of that, divide by the number of neighbors. Okay, that's d squared min. Okay, so it's the deviation from locally affine behavior. Then there's another one that we call delta squared min, which is d squared min. One issue of this is if you're in the solid, there's an elastic tail. If you have a little rearrangement, a non-affine deformation that's quite big, there can be a long-range elastic tail. If you take d squared min of all the neighbors, okay, and average that, it's d squared min of the particle I divided by the average over all the neighbors, scaled by all the average over all the neighbors. Then you get rid of that plastic tail, and you don't see it. There's a typo there. Okay, so that's how you quantify a rearrangement. There are many different ways of quantifying your rearrangements. Okay, but now the idea is you've got your hyperplane, okay, that separates the rearranging ones from ones they haven't rearranged for a long time. And now any new particle, I can calculate its local structural environment. I can put it and see what side of the hyperplane it's on, right? And I can measure its distance to the hyperplane. And its distance to the hyperplane is the softness, okay? And it has a sign, so that if I'm on the rearranging side of the hyperplane, it's positive. If I'm on the non-rearranging side of the hyperplane, it's negative.
Andrea,
Okay.
can I ask a question?
Yes.
Well, I'm a little bit confused by the fact that how do you define the hyperplane? Because you said that G is a correlation function based on structure, right? And then the colors are based on dynamics. Then the hyperplane, do you define it using this SVM method or using the
So what you do
structure?
with the hyperplane is, the way you do it is you say, for every particle that's on the wrong side of the hyperplane, I pay a cost. And the cost depends on how far I am from the hyperplane, how far I am on the wrong side of the hyperplane. So if I'm on the right side of the hyperplane, there's no cost. If I'm on the wrong side, there's a cost. Okay, and so then you have a cost function, which is this basically the sum of the squares of all the distances of the wrong particles from the hyperplane. And you want to minimize, you want to choose the hyperplane that minimizes that cost function.
Right, right. But I guess my question is, the line that you draw in your schema, the picture, is it taken from the structure? Is it right? Because G is a correlation function based on the structure, right?
G characterizes the structure.
So the hyperplane
So
is
this is a
defined.
high-dimensional space that characterizes the structure.
Okay.
Local
right.
structure on the particle. And this hyperplane, what it is in the end, okay? In the end, the softness, which is the distance of a particle from the hyperplane, the signed distance of a particle from the hyperplane, the softness is a weighted sum of G of R, or a weighted integral. And what we're doing by defining the hyperplane is to find the weights. We're minimizing a cost function to find those weights.
I have a separate question. If you go to where you define your d squared, yeah. So the affine deformation, in some sense that sort of minimizes things in a homogeneous material, but in a glass you could also define the forces or the stress, and you could try to minimize the stresses just by looking at the relative positions of the particles and the forces that they would exert on each other based on either the potentials or Brownian motion, right? Something like the Brady, sort of the way that we calculate the stresses for colloidal suspensions with salsa, or the way that Brady does it with his integral over the particle positions. Is that something that people have looked into as well?
Yeah, so you can look at the stresses. You can look at, so that's like the first derivative of the potential. You can look at the Hessian, the second derivative of the potential, or the third derivative. People looked at nonlinear derivatives. And you can do that, and you can come up with good predictors, okay? We're avoiding that because we don't want to have to know the potential, because we want to be able to apply to experiments. So that's why we're only looking at structure. So I'm not saying you can, and I'll show you explicitly that methods that look at, derivatives of potentials actually do better, okay, as predictors, okay? It's just that we're trying to avoid that. Then that was just a decision, which is, it depends on what you want. In our case, we wanted something that could be applied not only to simulations, but experiments. Okay. All right, so this, I just want to show you it does work. So here's a Leonard-Jones system. It's above the glass transition, and you see the particles fluctuating. Okay, and now we're going to color them by which side the hyperplane. So the red ones are on the positive side of the hyperplane, the blue ones are on the negative side of the hyperplane. And then we're going to peel away and just show the particles that are actually rearranging. Okay, and what you see is that they are, 90% of them are red. Okay, so this just shows the distribution. Here's the distribution of softness of all the particles. Okay, here's the distribution of softness conditioned on the ones that are rearranging. Okay, you see that there's a good separation between the two. All right, so it's, all right. Now, what we can do is look at the fraction of the particles in some interval of time of softness S that are actually rearranging. Okay, so it's really the dependence, how strongly this depends on softness that tells us how good of a predictor softness is. What you can see is that at high temperatures, it's always monotonically increasing the softness, which is good. Okay, the softer it is, the more likely it is to rearrange. Okay, and you also see that as you lower the temperature, okay, it becomes a stronger and stronger function of softness.
We have another question here.
And it's nearly exponential. Okay, this is the log of the probability versus softness, and it's nearly a straight line. And we're going to actually assume that it's exponential in our simple theories. Okay.
Hey,
All
Andrea,
right.
we have another question.
I just wanted to say yes, why we use delta squared min. So, yeah.
Hi,
Is there a
Andrea.
question?
Yes. I was wondering, you train your SVM on, well, data, right? So it's probably simulation data. So how much of your results depend on the potential you use for your training data? And how well can you, for example, extrapolate to new potentials you haven't used in your training set?
Yeah, I'll show you in a moment an example where we trained same hyperplane for two different potentials. But usually what we do is for each different potential, we have a different hyperplane. That's usually what you need. So if you change the potential significantly, you do need a new hyperplane for it. So it's not a universal definition. It really depends. What softness is depends on your system. And that's where, it's sort of unsatisfying compared to dislocations. Dislocations have a universal definition. Okay, but softness does not have a universal definition. But what's interesting is that the emergent properties of softness have some universality to it. So I'll get to that. Yeah, so, all right, yeah. this is great. These are all these are all great. I'm glad you guys are asking these questions. Okay. So what I said was we were only using a small fraction of our particles in our training, right? The ones that are actually rearranging and the ones that didn't rearrange for a very long time. But that's incredibly wasteful of data. And usually we're in this case where we don't actually have enough data. For example, if we're looking at experimental data, we really don't want to waste any. And this data can be very time consuming to obtain. So how can we be more thrifty? Okay, and that's where I want to get to delta squared min. So this is a picture of d squared min, and you see this is a system that's being sheared. Okay, and you see, oh, there was a little rearrangement here. Okay, and so you see the core of the rearrangement, but you see that way beyond the core, okay, you see this dark stuff. And it decays away. The darkness decays away. And in fact, it decays away as a power law from this due to the strain. Okay, it's elastic dipole. So what we do instead is we define delta squared min, and that's d squared min of particle I divided by the average of d squared min over the neighbors, j. Okay, what that does is it smooths out that power law decay. So if I just take I and I divide it by the average over the neighbors, I get rid of that power law tail. And if you look at delta squared, okay, it looks like this. You see things everywhere. You see all this other stuff starting to pop up. You see, you didn't see anywhere anything far from the rearrangement because the strain field just decayed away, and that was dominating everything. So now that we divide out that elastic tail, you can see this coming up, and now we can train on local minima and maxima of delta squared min instead of d squared min, and that's a lot more data. Okay, yeah, so local maxima. So that's method 2. And you can do even better, okay, by instead of doing a hyperplane, so that's called a support vector machine, is where you draw this hyperplane. Support vector machines, I think, were introduced in computer science in the 1970s. It was only then in the 2010s that we started using this. But so 40 years behind the computer scientists. Another thing that you could do is linear regression. Okay, and so then you can use all of the delta squared min, everything, and you just fit what's a line that best fits delta squared min. Okay, or e to the, so softness. We try to find the weights a sub I, okay, of our structure functions. So that's this is g of r, a different r, for example. Those are our structure functions. We want to find that the weights that best fit this. And then we use every single particle. That's the most efficient use of data. And then you fit this thing, and you look at the r squared, and it's terrible. It's 0.2. Okay, it's like, how can you get anything that has an r squared of 0.2, right? You're used to fitting lines and getting r squareds of 0.99, right? So this is bad, right? But actually, it's not so bad. So the test is, can you find the rearrangement? And so if you find the particle in each configuration that has the very largest value of d squared min, so the global maximum, okay, let's call that particle I. And now I'm going to make a rank list of all the softnesses of all the particles and see where particle I falls on that list. If it's always a softness, then it's number 1, okay? And so then you would get 100%, right? It would be at the very top of the list. And so the idea is you can average then over your configurations, and you can see where does it fall in this distribution. And so linear regression, yields 87%, the 87th percentile, quite high. And just picking local maxima and minima and maxima of d squared min, using those to train, or delta squared min, gives you 88%, almost no difference. So in terms of finding the particles that are actually rearranging, even though the R squared coefficient over the whole thing is terrible, to find the one that's actually rearranging, it's very good. Okay, so, and this cumulative distribution is something that we'll come back to as a way of quantifying how successful a quantity is as a predictor. Okay, so now the point is that we've got this hyperplane, or we've got this definition of softness, right? Which is this linear combination of my structural variables, or the structural environment. It's a weighted integral of the pair correlation function. And now we can say, what did it tell us, right? We trained it. What does it mean? What is softness in the end? Oh, sorry. Before I get to that, let me compare softness to other predictors, as I said I would. Okay, so there was, oh, this is totally the wrong reference. Sorry. The reference is by, the first author is David Richard, who is a hero. He collected all these things and compared them. So David Richard, and it was in Phys Rev Materials, and I don't know what year, 2020-ish, 2019-ish, I don't know. Okay, sorry, this is the wrong reference. All right. So what we did here, this is a paper that involved a massive number of people, all bringing to the table their favorite structural, or their favorite predictor of rearrangements. They're not all structural. Okay, so the red ones here, the ones tinted red, are purely structural. Okay, theta in particular is, you know, something that characterizes, it's sort of like size 6. It's a measure of bond orientational order. Purple is softness. They put it purple softness because we actually use, it's not purely structural in the sense that we use dynamical information to train it. Once we've trained it, it's purely structural. Okay, and you can see that the red, the theta does as well as the purple, but that's just because of the potentials that we use. We used, these were two-dimensional polydispersed. One was polydispersed, the other was a binary mixture of Leonard-Jones particles, so spherically symmetric potentials. And because they are basically spheres, this quantity theta works. If you had any other potential that was not spherically symmetric, the theta would not work at all. Okay, and then they had them prepared under different quench conditions. So here's softness, purple. Okay, it does fairly well compared to these other predictors. So these now depend on derivatives of the potential. Okay, everything beyond here, everything beyond the purple. And the purple doesn't do quite as well as you see, as for example, the green ones. Okay. Sorry about that. It doesn't do quite as well. We are going to, in fact, later on, I'm going to talk about training on this. This is the local yield stress, which does quite well. And I'll talk about that and talk about how we train on that. Okay. That does require knowledge of the potential, though. All right. So other ways of, other machine learning methods that we have brought to bear on this, you can do unsupervised learning, and that's not as effective as, so here, you don't use any dynamical information. You don't say, oh, I know which ones are rearranging and which ones are not rearranging, and I use that to find my hyperplane. What you do is, in this high dimensional space, you just connect each particle position, okay, in that high dimensional space to its neighbors with springs, okay? And then you just take it and collapse onto an arbitrary choice of 2 dimensions, okay? And then, and look at what you have. And so, and minimizing the energy, minimizing the elastic spring energy as you do that, So that's called t-SNE. That's used, for example, to distinguish handwritten digits or that kind of thing. So it's an unsupervised learning method. So you now collapse it down, and now you look at which ones were rearranging and which ones were not rearranging. Okay, and what you can see is that there is separation between the two. Okay, you have red and then you have blue here. In 3D, it's better separated like that. But there is some separation, and so even with this unsupervised learning method, you can determine something, right? So again, you have to, in the end, use that information about whether it was rearranging or not to draw these boundaries, but you can, but this part was done without using that information. Then you say, well, why don't you use a neural network? Neural networks are so great. Turns out that shallow neural networks don't do any better than the support vector machine. Deep neural networks can do a little better. We can go from about 88% prediction accuracy to 92%. Okay, that's not enough of an advantage to make it worthwhile, because with softness, with using the support vector machine, in the end, we know what those, we have a weighted function of G of R. We know we can have some physical intuition for what we're doing, for what came out, what softness means. But with a deep neural network, you don't have any new intuition at all for what it means. And so the slight gain in accuracy is actually not worth going with a method that's completely opaque in terms of being able to identify what softness means physically. Okay. Also, well, if you're training on images, you know, people really haven't done it for 3D or higher. It's only 2D. Okay. I should mention also graph neural networks are, if you're going to use a neural network, the natural way to do it is with a graph neural network. And that was a nice paper by Baps et al., where they were predicting dynamics way into the future at a relaxation time later, okay, with graph neural networks. But that's a paper worth reading, because graph neural networks, I think if you're going to use a neural network, that's the way to go. And that's a natural thing for if you've got a system of particles, which have positions. So their positions in space form a graph. And it's a very natural thing to use. Okay, so more generally, we don't just use G of R, we use this three-body term as well, which measures something about bond orientation. Okay, for just a Leonard-Jones mixture, it turns out that we get 90% accuracy. Okay, if we use 100 radial functions, so 100 different bins in G of R and 22 of these, but we get 88% accuracy if we don't keep these at all. Okay, so again, we often don't use this because it's not worth the extra gain in accuracy. Okay, to get something that's sort of opaque. But these three-body terms are absolutely necessary when it comes to training on something like silica, where there is strong, you know, bond, where you have tetrahedral bonding, and that bond information is bond angle information is really important. But for spherically symmetrical potentials, it's not. The amazing thing is that we discovered if we have a binary mixture A and B of two different sizes. So if we have a central A particle, we can get 77% prediction accuracy using just the height of the first peak of two pair correlation functions, the AA and the AB correlation functions. Just those two quantities, a linear combination of those two quantities, the height of the first peak, already gives you 77% prediction accuracy. Okay, so, and in fact, if you look at the accuracy as a function of the number of structure functions you keep, okay, as I said, so if you just have one peak, it's 64%, two peaks, it's GAA and GA. If you only have GAA, the first peak of GAA, that's 64%. If you have the first peak of GAA and GAB, that's the second peak. And as I add more, okay, structure functions, it gets slowly better, okay? And if you look at where the weights are the biggest, okay, they are at the peaks and valleys of the pair correlation function. So here's the pair correlation function, and where the weights are biggest in magnitude is at the peaks and the valleys, okay? And what is that telling you? The height of the first peak and the depth of the first valley, okay, in particular, are telling you the strength of the cage. So there's this old idea that what's happening in a glass, right, or glassy liquid, is that particles are caged by their neighbors. Then once in a while, they can escape from their cage. How caged they are is given by the first peak of the pair correlation function. The higher the first peak, here it is. Here are the correlation functions. Here are the pair correlation functions, okay? So here's what they look like, okay? So the black is for all the particles. The higher the first peak, okay, the more particles you have rearranged at that distance around your central particle. So the stronger your cage is. And if you look at the ones that are on the soft side of the hyperplane, that's the red, okay? You see they have lower first peaks and higher first valleys, lower second peaks, okay? So they have lower peaks and higher valleys. And what that says is that the soft particles have weaker cages. So in the end, when we define softness as a weighted integral of the pair correlation function, or weighted sum, it is simply a quantification of the cage, okay? And the softer it is, the weaker the cage. Okay.
There is a
So
question,
we've got this
Andrea.
predictor. I hope now you're happy. We can predict rearrangements reasonably well, but that's not our goal. Our goal is not to predict rearrangements, right? We want to understand glassy dynamics. So, so first of all, let's just ask, do we have hope? Okay, can we look at just the average softness and can it tell us something about a collective property? Okay, so this is where, in answer to the question earlier about potentials, okay, here are two systems of two different potentials. One is the Leonard-Jones interaction, and the other is the Weeks-Chandler-Anderson interaction, which is the same, except you take the system, you chop it off at the minimum, okay? You shift it up and you get rid of that attractive tail. So it's purely repulsive, okay? And it's basically the same. It's the same potential up to the minimum. Okay, at distances up to the minimum. Okay, just shift it up. Okay, so purely repulsive potential as opposed to potential that has an attractive tail. And this has been a famous exhibit, you know, the example that's always trotted out in glassy dynamics to say, oh, the potential makes a huge difference. Because these two potentials, which according to this theory of liquids, should basically be almost the same. And in fact, they have almost identical G of R's, okay, almost identical pair correlation functions. But they have completely different dynamics. Their glass transitions are really different. So if their pair correlations are so similar, okay, how can softness capture the difference, this huge difference in dynamics? So here's how similar they are. Here, the red is the WCA potential, the purely repulsive, and the blue is the Leonard-Jones with a bit of attraction. You see they're extremely similar, okay? But there's hope, right? I just showed you the difference between the soft particles and all the particles. That difference is pretty subtle too, right? But softness is weighting those differences to be important. So there's hope. And here's the dynamics. Here's the relaxation time as a function of what log of the relaxation time, right, versus 1 over temperature. And you see how different they are for the two different potentials, totally different. okay? And here's the average softness as a function 1 over T. Okay, they're different, okay, for the two systems. Here's the relaxation time as a function of the average softness, almost the same, okay? So here's the point, that we've used the same hyperplane for both systems, by the way. So the same hyperplanes, they're similar enough, their G of R's are similar enough. We use the same hyperplane, we train on both systems. The average softness, right, which is decreasing as I decrease the temperature, corresponding to an increasing relaxation time. So as I go this way, the relaxation time's increasing, I'm going closer and closer to the glass transition, okay? There's that tiny, tiny change in G of R, but that's what the weights pick up on. The weighting of G of R picks up on, and that makes the significant difference in the average softness, so that the relation between the relaxation time and the average softness is basically the same, very close in the two systems. Okay, so there is really hope that softness can tell us about this. Softness seems to tell us about, the average softness seems to tell us about the relaxation time or something. Okay, so for now on, I'm going to talk about softness in a continuum approximation. Okay, I'm going to think about softness as a continuum approximation. It's this weighted integral of G of R with maybe this 3-body term if I want the bond angle information. Okay, so that's the continuum limit of what I showed you before. Okay, and the point is that these weights are chosen to strongly correlate with rearrangements. So now let me tell you about the properties of softness. It's approximately Gaussian. Okay, even as you lower the temperature, the width doesn't seem to change appreciably. It's correlated, it's got spatial correlations, but they're short, they're on the range of a particle. Okay, so, all right. So now, what can we say about glassy dynamics? And remember, this is what we want to understand. We want to understand this change at the onset temperature, and how do you get stretch exponential super Arrhenius spatially heterogeneous dynamics. All right, so you remember I showed you this plot of the probability of rearranging, and it gets steeper as I lower the temperature. I'm going to show you the same data, but now organized in a different way, plotted in a different way. So this is the log of the probability of rearranging versus 1 over the temperature for particles now binned by softness. So the softest particles are red, the least soft are blue, okay? This is an Arrhenius plot. Oh, sorry, a Boltzmann plot. Right, and it's a straight line. I get a straight line when I single out particles against softness. So what that means is that I can write the probability of rearranging like this, that for particles of a given softness, there is a well-defined energy barrier for rearranging. Okay, as long as something that reflects the configurational entropy at that softness. Okay, and if I look at how these depend on softness, what you see is that the energy barrier is decreasing as I go to higher softness, right? Higher softness particles are more likely to rearrange. They have lower energy barriers. Low softness particles have higher energy barriers. Okay, but this is amazing because we can now pull out something about the energy landscape. Remember that energy landscape was 3-dimensional, e to the order n minima, but now I can pull out information about what is the energy barrier that particles are actually traversing when they have a rearrangement. That's delta E, okay? From a purely structural quantity that's fast to calculate. I don't have to do complicated things in that elastic band to find out the height of energy barriers in this really high dimensional landscape, which is impossible anyway. Okay, I can just do this and gain some information about the energy barriers. And this is general. Okay, it's not just true for the Leonard-Jones, it's true for silica. Okay, just a strong glass former, totally different system. These are jammed particles, particles with harmonic repulsions. If you look at them as a function of temperature at different packing fractions, it turns out that you can tune them from being strong to fragile. So from being Arrhenius to strongly super Arrhenius. So here it is on this is straight line here is Arrhenius behavior, strongly super Arrhenius is high curvature upwards. So for all of these systems, one single hyperplane for all of these systems, and you see that change of behavior, and yet for each of them, the probability of rearranging at a given softness is a beautiful straight line. It's Arrhenius. Here's a system that's actually sub-Arrhenius. This is the vertex model of tissues used by Lisa Manning and others to describe biological epithelial tissues. It turns out to be sub-Arrhenius. Okay.
Hey, Andrea.
Again, you see this nice behavior. And here's a system that's not a glass at all, that's not disordered at all. It's aluminum polycrystals. In aluminum polycrystals, again, the probability of rearranging is Arrhenius.
Hey, Andrea, can you hear me?
Yeah.
We have a question here.
Hey, Andrea, I have a question about your last slide. Could you please go back, please? I'm wondering if there's, what is the physical meaning where in this graph of log of the probability over 1 over t, where all the curves meet?
Yes. That's extremely interesting. That's brilliant that you saw that. And I will get to that in just a few minutes. Yeah. I'm running out of time. Okay, but all right. I think I will get to that before 10. Okay. Yeah, this is a little bit more about aluminum polycrystals. We don't have to get into that, but softness picks up all the right things that it should. It doesn't pick up defects that are not responsible for rearrangements. It only picks up defects that are responsible for rearrangements. So it's really useful across this whole, okay. All right. So, yeah. Let me just skip all this. Before I get to that onset thing, I just want to say something about aging, because remember I said, suppose you quench at time 0 from a temperature that's high, okay, to a low temperature at which we can no longer equilibrate completely. Okay, so below the glass transition. So this is what happens just as a function of waiting time. And here the particles are more red, they're red and more opaque. More opaque as they get higher in softness, and black if they're on the negative side of the hyperplane, and less opaque, more transparent. And what you see is that as you age the system, the softness goes down. The average softness is decreasing. It's getting blacker and blacker as you wait. So the structure is changing. Okay. And the cool thing is that for these are a bunch of different quenches. So as you wait, so this is a function of waiting time, the relaxation time increases, as I said, and the softness decreases, as I said. Okay. But if you look at the probability of rearranging as a function of softness at 3 different ages, they're on top of each other. And if I put the aging data in with all the other data, it just extends these curves. They fall on exactly the same curve. In other words, what's happening is that the relation between the structure and dynamics remains the same. It's still described by these Arrhenius curves, okay? But the average softness, the softness distribution is shifting downwards as the system is aging. So for particles of given softness, the energy barrier is not changing at all as the system aged. It's just that the average energy barrier is increasing with age as the system falls into deeper minima, because the average softness is decreasing. So that's that thing about falling into deeper and deeper minima, either as you lower the temperature, it's coming from the softness distribution shifting downwards. And therefore, you see higher energy, bigger energy barriers. Okay, so whether you're lowering the temperature or just following things as a function of age, below the glass transition, you know, it's the structural change that's important. So that's the point, that aging is really a structural phenomenon. Okay, so that the relaxation time, that place where they all cross. So if you look at this, what you see is that it's nearly linear, that the energy barrier and entropy barriers are approximately linear in softness. And if we take that seriously, the probability of rearranging, remember, has this form, it's Arrhenius, and these are linear. So now we can take these terms and we can rearrange them. We can arrange them into a term, which is Arrhenius, purely Arrhenius, and doesn't depend on softness. And then there's a term which is linear in softness. So this depends on structure, okay, with this coefficient, where these are these coefficients here. If you look at this, so this is independent of local structure. This depends on local structure, but at one special temperature, okay, where S1 over E1 is equal to T, this coefficient is 0, and the probability of rearranging is independent of structure at that one special temperature, okay? And it's below that special temperature that the dynamics become dependent on softness. Above that temperature, it turns out that softness is not predictive of rearrangements at all. It's flat. So let me go back to here. Yes. You see, as I raise the temperature, this becomes flatter and flatter. It becomes totally flat at the onset temperature and above. So above that temperature, softness tells us nothing about rearrangements. Okay. But below that temperature, it starts telling us something. Okay. And where's that temperature? That temperature is here, right? That's where all the curves cross, where the probability of rearranging does not depend on softness. That's where they cross. So that's T0. And now that's the onset temperature in this picture. Now let's compare to the onset temperature that people measured by the onset of spatially heterogeneous dynamics. Okay, totally different measurement. Okay, and the dotted line is where they're equal. Okay, they agree. Okay, so that's what the onset temperature means. It's where the dynamics start to depend on softness or structure, local structure. And it's below the onset temperature that you start seeing all these things, that the softness starts decreasing, so the energy barrier starts increasing, the relaxation time becomes non-Arrhenius, the dynamics become spatially heterogeneous. Okay, and I guess next time what I will do is I will go into the theory, how we use softness as basis for the theory, and we can then understand these behaviors from that theory. Okay, describe these behaviors with that theory. Okay, I'm running way behind where I thought I would be, but.
Okay, thank you, Andrea.
Danilo, was I supposed to leave time for questions?
No, no problem. I mean, we can take one or two quick questions before coffee break. Are there questions? Carolina has.
So, Andrea, thanks a lot. It's very nice. Actually, this dependency on the when the dynamics starts seeing the structure is very similar to what people with the mean field models like Giorgio Parisi and predicts, right? So your theory goes in the same direction as what they claim. Am I right?
Yes. Yes, I think it's actually quite, all of this is not inconsistent with the replica symmetry breaking point of view. Is that what you're asking? Yeah, yeah. No, I think it can be reconciled with this. And I think they could even define something like softness. And I wasn't going to talk about this, but it turns out that if you just have, we took particles with Hertzian repulsions, okay, and we looked at plasticity. So we looked at quasi-static shear. This was work by Sean Rideout. And we looked at it across dimensions, so 3, 4, and 5 dimensions, and we trained on softness. Turns out softness becomes just the number of contacts, the coordination number Z. So the local coordination number in high dimensions is softness. Just tells you softness. That particles with lower coordination are more soft, and so it becomes something. You know, that is something that potentially you could treat with this RSB approach, and try to reconcile all of this. It would be lovely if they did that.
Okay, we have one more question.
Could you please revisit the fundamental physical aspect behind why the dynamics start to depend on softness only below T0?
So I just say this is a discovery, and we wouldn't have known this to begin with. Okay, but the picture, but it suggests a picture. These results suggest a picture, and the picture is that at a high enough temperature, you don't care what the local structure is. The local structure is such that you've got enough temperature, you got enough fluctuations so that you can rearrange whenever you want to. And it's only below this onset temperature that, how easy it is to rearrange depends on how your neighbors are arranged, the strength of your cage. And that becomes more and more important as you lower the temperature. So that's more the picture that emerges from these results than something that we could have said a priori.
Does that temperature correspond with any of the other temperatures that people talk about in the glass literature?
No, it is exactly that temperature. So this is the temperature they talk about in the glass literature, where the dynamics start becoming super Arrhenius and spatially heterogeneous and non-exponential. So that's how they define it from the traditional way, and this is our measurement of it, and they're the same. So this is for Leonard-Jones systems of 4 different densities. And they're right on top of each other. So yeah, this is really truly the onset temperature that people talk about in the literature.
But that's experimentally. I mean, there are other theoretical. The question is that like theoretical temperatures, like mode coupling temperatures.
He's asking about mode
Right.
coupling
So this
temperatures.
is the mode coupling temperature is lower. So the onset temperature, if you go down in temperature, first you hit the onset temperature, then you hit the mode coupling temperature, then you hit the dynamical glass transition. Okay. And then the Kaltzman temperature is way below that. But so there are other relevant temperatures that people talk about in the theory of glasses, but this is one of them. The onset temperature is one of them that they talk about.
And if you had a
In the infinite dimensional systems, the onset temperature and the mode coupling temperature are the same. They become the same thing.
And what about if you have
and the glass transition is sharp. It's a well-defined thing. So in infinite dimensions, the T0, the mode coupling temperature, the onset temperature, the glass transition, they're all the same thing. So, but as you go to lower temperatures, they start diverging.
And how would the whole picture change if you had a macroscopically non-homogeneous system if you had a gradient in concentration of particles?
Yeah, then you would pick that up in the softness. You would see gradients of softness in the system so that you wouldn't see them be more or less, homogeneous. Of course, softness is correlated on the scale of a particle, but not beyond that. But, if you prepared your system in some other ways, you could prepare it, for example, with a gradient of softness, potentially.
Andrea, how robust is the system to the number of defects that couldn't have?
I'm sorry, you keep cutting out. I'm not sure why.
How robust is the system to the defects, the number of defects?
How robust is the system to the number of different defects? To the number of defects in the system?
That was the question, yes.
Yeah, so the properties are very dependent on that. So for example, if you take this system and you quench it very rapidly, then the average softness is quite high. But if you quench it very, very slowly, equilibrating, extremely well down to a very low temperature, then the average softness is very different, much lower. So depending on how you prepare your system, you can prepare it with more or fewer defects. And that makes a huge difference to behavior. So in fact, if you have a lot of defects, if you now shear the system, what you see is a ductile plastic behavior and avalanches, crackling noise. If you take the very well equilibrated system with few defects and very low softness, very low average softness, you see shear banding and brittle failure right away. So it really does depend, and that difference, you can see it in the softness field.
Okay, one more question by Ty, and then we go to cough break.
So one of the things that we're working on are actuators, and the way that they work is that we build very thin crystals. And the question that I have is, if I think about making the system polycrystalline on different length scales, that should allow me to tune the brittleness or the plasticity of the system, right? I mean, the more homogeneous crystal I have, the more plastic it might be. The smaller the grains are, the more brittle it might be. But you also have these sort of soft spots between the grains for the system to deform. I'm just trying to figure out what I should do when I'm making my thin films to make it more elastic and glassy. And can you use your softness parameter in some sense as a design criteria for building thin films that have prescribed properties?
Yes, this is something that we're very interested in, because I guess on Friday I'll talk about inverse design. I've had this in mind for a while, but we haven't done it. Can we use inverse design to design systems with high average softness? Because systems with high average softness are more ductile. Systems with low average softness are more brittle, as I was just saying. So can we design solids to have large average softness? And what are you designing? It's usually designing the preparation protocol. So you had to have a cost function, which basically maximizes softness during your preparation protocol, which is characterized by a number of variables, and then figure out what does it take. But for glasses, it's sort of simple. It's just you want to quench really fast. But for crystals, yeah, I'm not sure. I mean, it could be that, right? You have some. It's like work hardening or something. That you have some protocol of load that you apply in order to get it to have high softness. But yes, in principle, now that we know what softness is, and that high softness is good for ductility, then you could apply it to a system, and you could try to minimize some cost function to get as high a softness as you can for some preparation protocol.
Okay, thank you, Andrea. Let's thank Andrea.
So Danilo, so you guys, maybe what I'll do in case anybody had, if I were there, people could come up to me afterwards and ask questions. So
Maybe you can stay on Zoom.
yeah, I've got a
and
meeting